well, linears, quadratics, and absolute values, I should say, which all things that we come across are going to have parent functions. Ideally, you'll memorize. Olivia, why'd you just make a funny face at me? Ideally, you'll know just by instinct what these functions look like, what their parent graphs look like, so that you can move and shift and stretch and compress accordingly. If you don't, though, you can always do a table of values. So before we jump into this, anytime you forget, let's pretend you forgot what a line looked like. That's the parent graph for a line, and it's just y equals x. So you essentially just can make a quick table of values. If x is negative 2, this equals negative 2. If x is negative 1, don't do this. You don't have time for this. If x is 0, y is 0. If x is 1 and 2. And then you just plot those points, and that trend is your parent graph. Quadratics, same thing. If you don't know what a parent graph of a quadratic parabola looks like, just start plugging numbers in to your parent graph. Negative 2 squared is 4, negative 1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4.
I did the notes, not the quiz. I was wondering why I was so confused. Yeah.
Do you have a study hall today?
8th period.
Okay, I'll see you then. I'll be right here.
Can I have another notes?
Oh boy.
It's Tuesday.
Yeah, not Monday.
Thank you.
We'll survive. Okay. Actually, you know what I'd rather? Just take it now, and you can watch the video. Just ignore me. Is that okay?
Yeah.
All right. So when you go and plot those points, you see the parent graph of a quadratic. And lastly, an absolute value parent graph. So if you plug in negative 2, the absolute value of negative 2 is 2, of negative 1 is 1, of 0 is 0, of 1 is 1, of 2 is 2. And here, those points would give you the parent graph of an absolute value. So ideally, you know these shapes and you know what they look like. And as we move through the year, you will square root functions, log functions, which doesn't even sound like the same language to you, exponential functions. Ideally, you'll just know what they look like. But in a pinch, if you don't, number one, you actually could just plot the parent graph on your calculator and take a look at the tables. But if you didn't have a calculator, you could just come up with a table of values. And I like to kind of surround 0. So negative 2, negative 1, 0, 1, 2, and see what these values look like. So if I plug in negative 2, what's the square root of negative 2? No, not the square of it, the square root of it. What times itself gives you negative 2? That's what it means if you're asked for the square root. And the answer is, there isn't one. At least it's not a real number, which we'll talk about. So that is not even a point on the graph. You can't take the square root of a negative. So the square root of negative 1, nothing. Square root of 0, what times itself gives you 0? 0. Square root of 1, what times itself gives you 1? 1. Square root of 2, what times itself gives you 2? Well, you don't know that, right? It's going to be a crazy number. Square root of 2, this crazy number. I'm not even going to do that. What's the next nice x value that we can take the square root of? 4. And we get 2. What's the next nice number? 9. And if you do the square root of 9, you get 3. That should be enough. So there is no graph to the left of 0 because you can't take the square roots of negative. So the graph actually starts at 0, 0. This is the first kind of graph you guys are ever seeing that doesn't have an arrow on both ends. Okay? Lines have arrows on both ends. Parabolas have arrows on both ends. Absolute values have arrows on both ends. These do not because there's a limited domain situation. You can't take the square root of anything in the world. So that's a hard point, no arrow. And then 1, 1. And then 1, 2, 3, 4, 2. 5, 6, 7, 8, 9, 3. And then we can go on forever, but it's going to sort of even out and flatten a little bit. It will never be perfectly flat, but sure, it will look flat. Okay? So that's your parent graph. And again, like I said, if you ever forget any graph, square root of x, for example, plug it into your calculator, graph it, you can see it. You can see how even on the calculator it comes to a hard point and then continues infinitely to the right. And then you can look at your table and you can see what happens on your table. -2 gives you an arrow, -1 gives you an arrow, and so on and so forth. And you can just pick your nice point, 0, 0, 1, 1, 4, 2, 9, 3, and so on and so forth, and just grab a small sample of points from your table to graph an accurate picture. You good? Okay. Now, thinking about transformations, because everything is always, every family of functions, in this case radical functions. It says square root, but put radical. We're going to have to talk about vertical shifts, horizontal shifts, vertical stretch compression, horizontal stretch compression, vertical flip, horizontal flip, all those things that we talked about with transformations last week. So if you're adding 3 within the function, do you see how that's happening? If it's within the function, is it horizontal or vertical? Horizontal. So is that left or right? Left 3. Horizontal, left 3. Then there's a -2 after the fact. If it's outside the function, that's always vertical, up or down? Down. And both of these were shifts, we know, because of the plus or minus, right? If it was multiplying by 3, it would be a stretch or compression. If it was multiplying by 2, it would be a stretch or compression. Are we good? So all we're going to do is take those critical points, 1, 2, 3, 4 of them, and shift every single one of them left 3 down 2. And keep in mind that that origin, which was the hard endpoint, is now over here, so it still is a hard endpoint. No arrow on that end. We do have an arrow on the right end. Okay, you got to kind of track where's your hard endpoint, because that's still never going to go past it. So these concepts of transformations are going to thread throughout the year and only be slightly different based on where your parent graph's starting points are. Are we good? Okay. So what is the domain of the parent graph? So back to the parent graph table of values. The x values that you're allowed to take the square root of are 0 and higher. So your domain is, if you do set notation, x has to be greater than or equal to 0. If you do interval notation, that's from 0 and with a bracket, because yes, that includes 0, it can be that, to infinity. What were the y values limited to on your parent graph for our range? Right, they started at 0 as well, and you can almost look at the picture. The range starts at 0, and it's going to go to infinity as well. It's not going to get there quite as fast because this kind of flattens out, but it can, because x can get to be 5 billion, right? The square root of x will be, in that case, I don't know, 100,000. It will keep growing and growing, although it's slow. The range is unlimited up top as well. So the range goes from, set builder would say y has to be greater than or equal to 0. Interval notation would say 0 to infinity as well. Now, your new function was g of x, and its new domain came after some shifts. So anything happening horizontally is going to affect your domain. That's your x-coordinate. Anything happening vertically is going to affect your range. So as far as your domain is concerned, and we have two kind of vantage points here. We could just look at the graph to see the new domain, or we could just think about the old domain shifted left 3, right? The old domain shifted left 3 would now be from -3 to infinity. Don't we agree that infinity shifted left 3 is still infinity? Okay. And your range, because this came down 2, that's 0 is now going to be a -2 to infinity. And obviously, if you look at your graph of your g of x, you can see that. -3 is now the furthest left to infinity, and -2 is now the furthest down to infinity up. Okie doke? Okay. Take a minute, see what you would guess for number 2. Keep in mind that the original graph, and I'll sketch it on here, looks like this. That's the original. So you got to kind of figure out, well, what transformations happened to that. Chris?
Is there a negative on number 1 in front of it?
Yes, there is. Yep. Yeah, it kind of blends in with it. But the first one is negative square root of x plus 4. The second one is 4 minus root x. And we will prepare to take a vote. By holding up 1, 2, 3, or 4. Okay, on the count of 3, hold up 1, 2, 3, or 4. On your mark, get set, go. I see 1s and 4s mostly. Mostly 1s and 4s. So, very similar. They both have negatives out in front, which is good because there's definitely a flip, and it's a vertical flip. So there should be a flip, a negative out in front. The question is, the number 1 says plus 4 in the radical, and number 4 says minus 4 in the radical. Now, we all know that it shifted left 4. We can see that, right? Flip down and left 4. Left is horizontal, so we were correct to have it underneath the radical. Now, your gut would tell you left 4 would mean minus 4. But because it's horizontal, it's backwards, right? So the answer was 1. Truthfully, on a multiple choice exam, you have a calculator. You could type all of those in and see which one looks like that. It's an option, okay? It's not the way conceptually we want you to do it because they'll find tricky ways to ask you on the regions how to do things without being able to use your calculator. Like they might have x plus a, and they'll say a has to be a positive number. So they'll have an x plus a option and an x minus a option. You can't just type that in your calculator. So you do want to hear out and understand the reasons why without the calculator, but certainly if you can use a calculator, I don't want to take that away from you. Exercise 3. Which of the following values of x does not lie in the domain? Okay? So we talked more about the domain on the parent graph, and then after we shifted it. And you can still do that here. The domain on the parent graph is from 0 to infinity. This thing shifts at how? Right 5. So how is that going to affect your domain? Is it going to affect your domain? Yes. Right 5, anything left, right, horizontal is going to affect it. It's going to make it 5 to infinity. So which one of these does not lie in that? 2. Okay? Generally speaking, and here's another way of thinking about it. You can only take the square root of something if it's not negative. In other words, if something is not negative, if x minus 5 can't be negative, then it has to be greater than or equal to 0, right? Then you just solve that, add 5 to both sides, and x has to be greater than or equal to 5, and again, only 2 doesn't satisfy that. Are we good? Okay. This one is a trip. I'm actually going to skip this one for now. Just maybe I'll start with that tomorrow. But exercise 4 is going to sort of piggyback on what we just talked about. Determine the domain for each of the following. Now, based on the shift left 2, I can do this one in that fashion, but these are not going to work so well that way. I have to actually do these this way. Anytime you're asked for the domain of a radical function, just take whatever's underneath the radical and make sure it's greater than or equal to 0, because those are the only types of numbers we are allowed to take the square root of. So on B, that would be taking 3x minus 2, setting it greater than or equal to 0. And on C, that would be taking 8 minus 2x and setting it greater than or equal to 0. And then you have to solve them to figure out what x can be. And I'll just solve C. They're all pretty equally as easy. You'll see in a second why I'm going to pick C. If I want to isolate x and solve for it, what do I have to get rid of first, Morgan? Good? Yep. Subtract 8 from both sides, so negative 2x is greater than or equal to negative 8. Next step. Divide by negative 2. Eric, can you tell me something fishy about this? Who remembers inequalities? Olivia. Anytime you multiply or divide by a negative number, you have to flip the sign. That's one trick with inequalities to remember from Algebra 1. So in this case, x actually has to be less than or equal to 4. You know how you can check, by the way? Type it in. Square root of 8 minus 2x. Look at it, and look at your domain. It's x is less than or equal to 4. See that? Okay? These transformations are somewhat complex and beyond what we have to do. The fact that there's a horizontal dilation and a horizontal shift, we really don't do that. You'll notice you'll never have a combo of that, and it's not really in our curriculum because it's a whole nother layer of stuff. So you'll have to do those that way. Okay, last one. Write the inverse of the function given by f of x. Sierra, are you done yet? Okay, so on this particular one, there is a process involved, obviously, with writing an inverse. Just like transformations, we're going to do it with every single function type. Same thing for inverses. It's switching that x and y and solving for y. So how would we get y all by itself here? What would have to come first? Lucas?
You have to square both sides.
Yeah. You can't subtract 2 over yet because it's all locked up underneath a radical. You actually have to get rid of the square root first. And the opposite operation of square rooting is squaring. So we're going to square both sides. And what's nice about the square root side of things is the square and the square root just cancel. Now we can subtract the 2. And we're pretty much done. I just have to rewrite the proper notation. Rather than y, I'm going to say f inverse of x equals x squared minus 2. So a quick graph of each function. The square root of x plus 2 is shifted left 2. So it's going to be something like that. The inverse function, which is x squared minus 2, is a parabola shifted down 2, yes? So shift that down 2, and it will be something like this. Okay? I'm going to pass out your homework, and we will start with this tomorrow.